Why is the electron's magnetism always just a little stronger than our best theories say it should be? In the energy filament theory, that tiny extra magnetism is not a mistake in the math but the way an electron quietly reports how the underlying energy C is being stretched. In textbooks, the electron is the well-behaved child of particle physics. It is light, stable, does not decay on its own and, on paper, looks like the simplest building block in the zoo. So its magnetic moment should be the cleanest solved problem. In this picture, the electron is a loop of filaments held up by the energy C, with a steady flow of energy running around the ring like water in a tiny circular channel that never spills out. Its electric charge tells you how much push or pull it exerts, and its magnetism tells you exactly how that internal river flows and bends. Quantum theory and quantum electrodynamics have spent decades calculating that flow in crazy detail, stacking spin effects and higher order corrections until they produce a magnetic strength that is often called the standard answer. Here is the strange part: when experimentalists measure the electron's magnetism with ever more precise devices, the result is not random, it is consistently a hair larger than that standard answer, always off by a tiny but stubborn amount, like a ruler that is always longer than the printing on its edge by half a millimeter. The usual response is honest and careful. The theory must still be missing very subtle higher order loops and quantum fluctuations. And one day, when every last correction is added, the numbers will match exactly. Yet round after round of refining the theory and the measurements has not completely erased the gap. It has pushed the disagreement into a finer corner, but a faint residue of too much magnetism remains, like background noise that never quite goes silent. In this view, that is the point where we should ask a different question. Maybe the electron calculation on a perfectly uniform background is right for an ideal world, and what we are seeing is the electrons responding to a layer of reality we usually treat as invisible, the shifting tension of the energy C it is living in. In this language, the internal energy flow is not frozen by the equation. It is shaped by the local tightness and tiny ripples of the sea. Change the tension even slightly and the most efficient route for the flow shifts too. Some parts of the loop become smoother channels where energy runs faster. Other regions are squeezed so the stream bends more sharply and a little side current appears. And the overall pattern of circulation ends up just a little more tilted than the ideal perfect circle. You can picture a river that looks calm from the bank but runs over a riverbed that is slowly being pressed and loosened. Press the bed here and the water speeds up in that stretch. Let a patch sag slightly and a small eddy appears there. To your eyes, the river is the same. Yet careful measurements of speed and swirling say otherwise. The electron is like that river. Its internal flow is extremely sensitive to the tension under it. So when the energy C tightens or relaxes a bit, the circulation quietly rearranges itself, and the magnetic moment grows by the same tiny amount, consistently above the ideal value you would get on a perfectly flat, perfectly uniform bed. In the earlier clues we saw electrons changing their timing in atomic clocks. The protons change their effective size in the radius puzzle. Neutrons adjust their lifetime between bottles and beams, and positronium shortens its dance on different floors. In this episode, the electron is using magnetism to say the same thing in a different accent. The common message is that particles are not dead parts. Each one is a loop or knot that listens to the tension of the energy C and answers in its own language. Sometimes with periods, sometimes with sizes, sometimes with lifetime, and here with just a bit more magnetic personality than the ideal. If those tiny extra bits keep showing up in lab measurements and in the light from distant galaxies, they are not random glitches. They are signatures of particles slowly evolving with the universe instead of hanging untouched above it. Tap follow, share it on New Physics, Clear Universe.